simulation of human intelligence processed by machines, especially computer systems. This session will be handled by Dr. Karthikeyan Chittayil, scientist NPOL Kochi. He has worked as a professor at Mangalam College of Engineering, Rajagiri School of Engineering and Technology, and he was also former chairman of Amrita Vishwa Vidyapeeth. We are really blessed to have Dr. Karthikeyan Chittayil sir to this program. I would like to invite Ajmi S, Women in Engineering, Secretary, IEEE Student Branch, College of Engineering, Perumon. Ajmi, please.
Good evening, one and all. A very warm welcome to all those who have joined here for this section on artificial intelligence conducted by IEEE Education Society Kerala chapter in collaboration with IEEE EdSoc SBC College of Engineering Perumon and IEEE SB Musiliar College of Engineering. With great pleasure, I would like to welcome our speaker, Dr. Karthikeyan Chittayil, ScientistE retired, NPOL Kochi. He has worked as a professor at Mangalam College of Engineering, Rajagiri School of Engineering and Technology, and he was also the former chairman of Computer Science Department, Amrita Vishwavedam. I would like to welcome I would also like to welcome the professional execom of IEEE EdSoc Kerala chapter. Also, I welcome the student execom of IEEE EdSoc Kerala chapter. Finally, I would like to welcome Tasneem ma'am, branch advisor CE Perumon, and Shimi Mohan, branch counselor, Musiliar College of Engineering. Also, I welcome all the participants who have assembled here for the webinar. Now, I welcome Kavya KS, MDC Kochi Hub, IEEE EdSoc Student Team Kerala Chapter for providing a brief introduction on our prominent speaker. Thank you.
Thank you, Sri. Good evening, one and all. It's a great pleasure and honor for me to make a quick introduction to Dr. Karthikeyan Chittayil, our distinguished facilitator for the day. Dr. Karthikeyan is a retired scientist from NPOL Kochi. He took his MSc Engineering from the Indian Institute of Science and PhD from Penn State University, Pennsylvania. He has served as a professor, chairman, and computer science department at Amrita Vishwa Vidyapeeth, Coimbatore, professor and head of the department at Rajagiri School of Engineering and Technology, Kochi, and as an adjunct professor at Mangalam College of Engineering, Ettumanu. He retired as a scientist from NPOL Kochi in 2001 after serving for 25 years. Today, it's a great honor for us to have him with us as a resource person for this session. So, with great pleasure and respect, I invite Mr. Sripad Kamalkar to take over this session from here. Over to you, sir.
Hello, good evening to everyone. Thank you for the very nice introduction. As you all know, this subject is a very broad subject. A lot of new things are happening, and my attempt will be to give those of you who have not much idea about artificial intelligence some basic idea about the subject, some of the different aspects of artificial intelligence, and then try to look at some of the latest things that have happened in this area. Of course, I won't be able to cover many of the things that you might be seeing in many videos like robotic dance and all that, that you can very well see if you go to internet and look for Boston Dynamics. You can immediately go to the company's website and they will show you so many different aspects of the robots doing dances, they're taking moving things from one place to another and all that. First of all, when I saw that, I thought it was just animation, video animation, but it's not. It is really real robots doing that work, and it's really surprising that such things can happen. In fact, when I worked in this area, when I was doing a PhD, nothing much was possible like that. In fact, at that time, one university in US was trying to have a robot walk on the surface of the lab. I mean, just the lab floor and they were failing. But now there are robots which can walk on any rough, uneven ground. So, and that's a very great jump in the kind of technology. A lot of new learnings happen. So I will not be able to cover all that. I will just show you, go through slides and show you the beginning of AI and some of the aspects that people are discussing and researching now. Okay. Okay, I'll go to the slides now. Are you able to see this? Hello?
Yes, sir.
You're able to see
No,
the
no, sir.
slides?
It is not shared.
Okay,
Not shared, sir.
okay.
Hello.
Yeah.
Yes, sir. Sorry, can you please share once more? Try to.
Okay, okay. Some problem is there. Are you able to see that now?
Sir, the presentation option is not activated from the Google Meet. That's the issue.
Okay, okay, okay. Just a minute. Okay. Are you able to see that now? Hello?
Yes, sir. It's coming up. Yes, yes, we can see.
Okay.
Hello, everybody, please wait patiently. He will be joining in a while. Sir, your mic is on mute.
Hello. Sir, please click on the mic. Yes.
Yeah.
Yes, we can hear you.
Okay. You are seeing the presentation also.
So we can see the screen only. So please click on the PowerPoint window again and go to slideshow. So no need to off the
Okay.
presentation. Just need to open the uh, you know from the taskbar.
Okay.
Yeah, just click on the PowerPoint option. Go to slideshow.
Okay.
At the top.
Okay.
At the top, there is an option called slideshow.
Yeah. Okay.
Yeah, from beginning.
Okay.
Okay, sir.
Are
It's
you seeing
running.
now? Okay.
Yes, sir. It's fine. You
Okay.
can start.
Okay. Thank you. Okay. So first, this slide shows that AI systems are capable of storing knowledge, solving problems, applying that knowledge, and acquiring new knowledge from experience. And this is what we also do, right? So the key components of AI systems is one is representation, that is how you represent knowledge in a computer. Then reasoning, how you manipulate that stored information, that's what called reasoning, and to extract new information from that. That is called learning, right? So these three components are the main components of any AI system. Okay. For representation, there are different techniques. One of the oldest technique people started with is symbol structures. That is representing our concepts and ideas as symbols, and then the relation between those as some kind of arcs or something, and it's possible to represent. We'll see examples of such a presentation. You can represent general knowledge, domain knowledge of a particular domain, or specific problems knowledge also using that. The different types are like you can have rule-based systems where you store information or knowledge in terms of rules, and sometimes it can be in terms of the procedure or algorithms which tell you how to proceed getting that information. So the reasoning is the ability to solve problems, express and solve broad range of problems, extract explicit as well as implicit information from the stored knowledge. And you can see that many of the applications of or the method of doing this on a computer can be represented as a search problem solving as a search. There are different mechanisms by which you can go do the search. So you have to know which operators you have to apply to go from one search point, location point to another, recognize the solutions, etc. So we will see example of this from the next few slides. Okay, in learning, there are, again, in general, we can talk of learning as in getting general rules from raw data. Deductive means specific facts from general rules. Similarly, then similarity-based learning, explanation-based learning, problems in learning, various problems are in learning is there. So we look at those things also. The use of experts and expert systems. These are the things that we'll discuss. Okay. First, representation examples. One of the ways to represent some information that is using predicate calculus. Okay, you may wonder why it is called calculus, but here I'm just saying the basic elementary method of representing a relation between two people using this father bracket Albert Buchanan, saying that one is the father of the other. Albert is the father of Buchanan. Similarly, friends George, Kate. Here you can see that this relationship friends is a two-way relationship. When you say George is a friend of Kate, Kate is also, the reverse is also true. But in the father case, it's a one-way relationship. Okay. So similarly, from these two relations, like the father AB, mother AC, I'm just putting arbitrary. You can get to the new relationship that B and C are married. That is, if B is the father of A and C is the mother of A, then B and C are married. That is the information that we get. It's not given from the two information that father A, B. I'm just giving a simple example of how you get new knowledge from the previous. But you can have very complicated relationship represented by using this, and also very complicated new information gathered from this kind of methods. So predicate calculus is a very powerful method. In fact, some of the unsolved problems in algebra were solved by this method. That is, new mathematical theorems were generated using this. Okay, so if-then rules. This is something that we all know very easily. We understand. If it's cloudy, then it may rain. If it's sunny, then we can play football, like this. So this is also one way of representing knowledge in a computer. This is another example. It's called semantic networks. Here, actually, things can be related to each other through this kind of structure. So, for example, kingfisher is a bird. So that relationship that it's a bird is through a link, and bird has certain properties. It has feathers covering it, property. It flies. It is a vertebrate, and all this information, all these properties of the bird, automatically is acquired by kingfisher when it's related is saying that it's a bird. Similarly, some other properties kingfisher has, that is small bird, it's a colored blue, etc. So it is possible to represent a relationship between objects, ideas, etc. through this kind of relationship, semantic network. So that is one of the methods in which this knowledge is represented in a computer. Now let me look at how state space search can be considered a general way of solving problems. Okay. This is some kind of abstract concept, but then it's very powerful. You can represent, I hope many of you are familiar with the graphs, etc. So there's no difficulty understanding it. So you can represent the states of a particular problem as n set of nodes. Then A is the set of arcs linking those. S is a subset, contains S is a starting state, that maybe one or more subset of n, and GD refers to the goal state or the a destination state, which again is a set of states within that n. Okay. You can look at this particular simple graph. Here you can see that from starting from goal or the state, which may be a goal state, the one may be a goal state. From there, you can using certain operators, you can go to the state 2. From there, you can use other operators to go to 5, 6, etc. Similarly, go to 3 and all this. Now, any problem which can be represented this way, can be searched. That is, you can find from a starting state, you can find the goal state by searching through this. There are methods like deep depth first search, breadth first search, and there are many other heuristic search, etc. methods. I'm not going to go into details. You can find it anywhere in any AI book. So this is a very powerful method of searching through data, and data can be stored in whatever format, like one of the representations that we just looked at. So now look at a simple problem or actually a game that people play, 8 square problem, where there are tiles marked 1, 2, 3, 4 of 8 around. In the middle there is a blank space. So you can move the tiles by horizontal or vertical movements. You can see that the tiles 8 and 4 can be moved by left or right movement. 2 and 6 can be moved up or down or up. So by doing this, you are going to a different state. So this may be the goal state, and you may have another state which is obtained by moving these tiles around. Now the question that I can have is, how do you go from an arbitrary state given to the goal state? What are the moves required? This again is a very interesting problem which can be solved by this kind of searching. But these searches are generally called brute force methods. That means you are searching for all possible states and seeing which is the goal state. It is of course very time consuming, as well as it takes a lot of computer memory. So there are techniques like depth first search, breadth first search. They are all brute force searches. They search the tree in a particular way, but then both are, in fact, depth first search takes a lot of time, whereas breadth first search requires a lot of memory. So when and there are many methods of combining this, which may improve your memory and time requirement, reduce the thing. There are other methods of reducing the search space by so-called heuristics or thumb rules. I will not go into that. So this is something else. Reasoning with uncertainty is another method. It's not related to state space, where you can use probabilistic reasoning, and there are some techniques like belief propagation, Dempster Schaeffler. I'll not go into all these things. Okay. Now I just show you how an expert system works. Okay. It's the basic structure of an expert system. There is a user interface. There's an inference engine. This is the one which actually does all the thinking, really. Okay, and this knowledge base is the one which stores the information or knowledge. And there is a knowledge base editor where you can modify this knowledge. You can add new knowledge or subtract some of the information which is stored. Also, the user can query the system with some questions, and this engine will look into the knowledge base and see if it's an explicit information, it will give it to the user, or if it is to be found out implicitly, that it has to go through some process of searching in like the way you search in the tree we showed, and then also once it gets the answer, it may also require to give an explanation of how exactly it went through this. This kind of systems have been made to do diagnostic, medical diagnostics. It can be, it has been developed for doing some chemical analysis, try to design new chemicals for pharmaceuticals and other things. So this is again very powerful method. But again, ultimately it depends on how well you are able to store the information and how well you are able to use the inference engine to search that knowledge base. Okay. So here I'm showing the conventional, on the left side, the conventional approaches using this, whatever we are discussing now, which is actually based on some idea of how we think. That is about what idea we have about the way we think. It is based on psychology, based on that is other medical sciences, and I mean psychiatry, all those things, and also the way we use language, how we think logically, all these things. But that is the conventional way in which AI was done for a long time. But the other approach using what is called neural networks, it's a different approach that it actually tries to build up on the fact that ultimately the thinking that we do is from our brain, which has got a lot of nerve cells. So how the nerve cells behave, trying to model that in a computer and try to see if that model can be made to do similar things that human beings do. And that initially had a lot of trouble, mainly because the ability to store information and also the processing speed of computers was limited. But recent last 20, 30 years, the whole thing has changed. We are able to store almost unlimited amount of information in a computer, and also compute extremely fast way. So it's possible to do this kind of computation now with the present day. And this has led to some of the latest developments in artificial intelligence, like you might have heard of all this deep search and all that, deep learning and all that. Okay, so we'll first look at how the AI that is based on neural networks works, and then look at some other aspects like language, that is artificial, how language knowledge can be the language learning, etc. can be done. Also, some aspects of machine learning we look into. So this is about artificial neural network. The original concept of neural network was developed by some person like McCullough and Pitts in 1943. What they actually did is they actually tried to create an electronic circuit where you could give some inputs like x1, x2, weigh them by some weights, then sum it up, and it's a threshold theta, and then the output can be given to another function, which is called it can be some function which basically it limits the output of this to between 0 and 1. So you know this function f net is 1 by 1 plus exponent of minus output. So this will be a function which will be having a maximum of 1 and minimum of 0. So this was used as a model for the neuron, even though the biological neuron is much more complex object. Okay. So this was a method of training this neuron, which Rosenblatt in 1962, developed by Rosenblatt in 1962. Basically, what it does is modify the weights based on the output. That is, suppose for a given input x1, x2, you expect this neuron to give a output y, which is equal to output D. That is, the desired output is D. So the actual output Y and the desired output D, the difference we call it as the error, and that error is used to modify these weights so that ultimately the error between the difference between D and Y is as minimal as possible. So this method of training, it's a very interesting thing, and this was later used by many electronics and signal processing people for doing there is some kind of adaptive processing, filtering, etc. So we'll see how. Okay, I'll jump the. Okay, that file, that's something else. Okay, this is the method of mathematically. We can represent the error function as a function of the weights. That is the squared error. Okay? And if you find the derivative of this with respect to the weight, okay, the weight here taken as a vector. So this actually this means dE by dW1, dE by dW2 as a vector is equal to this, and so you get this by modifying this weight by adding some term which moves the in the opposite direction to the gradient. So this is the gradient which delta E change which shows the increasing direction of the error. So you modify that error by, by the weight by an amount in the opposite direction so that the error is minimized. So this way you use this iteratively, and you can finally reach the minimum of the, that is the idea, okay, minimum of the error function. So this method is called the LMS algorithm, or least mean square algorithm. Basically, you are minimizing the mean square error. And using this method, you can separate two classes of data. That is what the neuron can do. A single neuron is able to separate two classes of data like this. And mathematicians would say that to be able to separate two classes of data this way, you have to have the convex hulls of the pattern classes to be disjoint. That means these two classes, this pink class and this, should be disjoint. They should not have an overlap. But you may see that it is only in 2 dimensions. I have represented 2 dimensions, but you can imagine that even higher dimensions, 3 dimensions or higher dimensions also, you can think of a separating plane. In the case of 2 dimensions, this is separating. This is just a line. It's separating these two. If it is 3 dimensions, it will be a plane, normal what we call as a plane. But if you go to 4 dimensions or higher dimensions, this will be a hyperplane. But the separability, linear separability, as a very real thing, and it can be done in any number of dimensions. So the fact that a single neuron is able to do this kind of separation of data into the classes is a very important idea, and that is what has been extended in later to make a more complicated neural networks. See, for example, here I have shown a set of points, the pink squares and the blue circles, okay, which are separated by this red line. This red line is able to separate these two. Okay, and this line has the equation w1x1 plus w2x2 minus theta equal to 0, which means on this line shows this this quantity is equal to 0. So if you go to move to one side, this is positive, the other side it is negative. So by using this, you can classify to such not linearly classifiable material, that is data. Okay. Now you look at another case where the data is such that you cannot separate them by a single line or single plane. Here is the data you are having here is not separable. So you need to have more than one such line to, but these two lines, the blue and this pink line, together will be able to separate the data. Okay, so you can see that this effectively takes you to a situation where you use not single neuron but two neurons. Okay, and they together can be used to separate such linearly non-classifiable data. And this is the idea which is extended to multi-layer what is called feed-forward neural network, where n-dimensional data is input, and through a certain set of neurons, the output is taken to here. So here again, we do the same thing, similar to the single neuron. You give an input of x, then you have the desired values for all these outputs, and you can calculate the error and use the error to correct these weights. The method of doing that, it's a very, originally they thought that it is very difficult to find that kind of algorithm which can do that. But a scientist named Verbos was able to find a method called backpropagation learning or error backpropagation learning, which did this. So I'm not going to go into details of that. So that algorithm was able to make a very general approach to this kind of neural network. In general, this is called what we showed earlier is a gradient descent method. You have you can modify that using variable step approach, that is adjusting the steps using knowledge of the error surface. That's a problem called local minima problem. There is sometimes you find the error surface doesn't have a single minimum, but more than one minima is there, in which case you cannot use these methods. So there are different approaches required. In fact, the only way in a general case we can find the final total minimum for a function or using what is called global optimization methods. So there are different global optimization methods. We are not going to discuss that. I am just indicating to you that modern neural networks use this kind of global optimization method to find the correct answer. And some of the global methods are taken from nature. You can see in nature there's something called annealing. That in metallurgists will know how you can change the properties of material by doing annealing. And that annealing can be simulated in a computer to generate a new or better results. Similarly, genetic algorithms. This also does by using the basic theory of genetic modification, which is supposed to give you new generation of better qualified beings. That this is also used. Then there are so many other ways like biologically inspired computing and Karthikeyan optimization. These are all methods. And there is one which I have used earlier. It's called the guided evolutionary simulated annealing. In fact, this is a combination of evolutionary or a simulated annealing with some evolutionary methods. Okay. GESA that you can find, if you search literature, you find this. This shows some other neural network which use nonlinear method. That is, it uses feedback is also there. Earlier neural network I showed there was no feedback. Here they use feedback, and this makes a very complicated kind of interesting. It has got particular uses, like it's able to store imperfect data and create the correct data from that. Like if you have damaged computer disk, you can feed this into such a system and create the correct information, etc. And another interesting thing that I want to show is called self-organization, which is where there is no desired values given. The network is just able to learn either from the data some properties of data and present it in a interesting manner. So I'll give you the example. I will not go into this. This is called the coherent self-organization map, or SOM. And the interesting results using this map is if you give inputs, again I'm giving examples in 2 dimensions. You have a lot of random data taken from the 2-dimensional area and fed to this network. Initially, the network will, all these network weights will be around this center because they are taken as initiated small values. But once the network starts learning, this network starts unfolding from the center and finally reaches this stage where it is effectively almost covering the square area. Now, what is interesting is that instead of giving this data from the square, we had randomly given this data from this circular area. That is, all the data inputs are given from this circular area. Then the net will finally settle down itself to a circular distribution. Similarly, if it is given from a triangular area, that is, no data was from this side, only data from this side, then it also settles into a triangular shape. So you can see that this, without any training, without any input from the human side, from the data itself, the network is able to learn about the pattern the data has. That is the relation between the various aspects of the numbers. So this is another pattern which was fed like this, and you see the net finally settled down to a pattern which it has been shown that you can even do this for 3-dimensional data. That is, input was given from objects having three-dimensional property. That is like one example I've seen is a cactus. The cactus plant, points from its 3-dimensional points are taken and mapped into this kind of thing. Then it actually, the net converges into a map, like a picture of this cactus plant. So that is just showing that it's possible, even without any desired input to be given, a network to learn some aspects of the data, and it's also compress the whole data information into a smaller dimensionality. So this is very important in data compression, and in fact this coherent map and similar methods are being used for compressing large amount of data into smaller data, and which is very important in signal processing. So I'm just summarizing all this. Artificial neural networks, branch of artificial intelligence, first proposed by Turing, 1948. Okay. Simplified model of biological neural networks. The subject of current neuroscience research is minimum degree of neural network model complexity required to reproduce some resemblance to human intelligence. So this is what course, this was from around, I think, 2006 or 2010, but it has all changed now. These are general areas of application of neural networks, functional approximation, time series prediction, obviously, data classification, data compression, blind. All these applications, we can use neural networks and for system education, pattern recognition, radars, and all, etc. Medical diagnosis, data mining, all of this. Okay, but even though, despite all this, we find that there are many failures using the AI method. Even recently, about 2006, 2010, many of the things that AI people wanted to do could not be done. For example, summarization, which means basically we are given we are given a essay or something that we are asked to summarize into a small paragraph. It's very difficult for a computer to do. Translation, simultaneous translation, that is, as soon as the input is given, translating into another language, that is also very difficult. Automation driving in city traffic, that is, in city traffic, driving without a car or vehicle without a driver using a computer, that was also considered very difficult. Then a tennis playing robot, all these things were attempts made about 20 years ago, and it's failed miserably. But today, almost all these are being done. Okay. I think I will not go much into this. Fuzzy logic is also very important area which is used in neural network. In fact, AI research. People combine fuzzy logic along with neural networks to do a lot of things like neurofuzzy computing, all this. So it will not look into that, but I will just give you a basic concept about the purpose of fuzzy logic. Very often, okay, this is all not needed. I will just go into. Okay, this is just indicating the way in which the AI, what's called the machine intelligence quotient, like intelligence quotient that of IQ. So for a machine, this ZA, LA ZA, who is founder of LA coined this term, machine intelligence quotient, and he says that by 2000, this has reached there, and by some level, maybe 2000, maybe 2030 or something, he's expecting that human level intelligence will keep up possible for the machines. And here you can see initially it was all logic-based AI, symbolic AI. Later on, AI is a symbolic logic plus probability theory. Now they are using fuzzy logic, etc., which is basically perception-based AI, which improve the performance of the AI systems, and this improve this machine intelligence quotient to much higher values. This just sums up more or less the idea that you can see humans have a remarkable capability to perform wide variety of physical mental tasks without any measurement and any computation. Whereas, for example, driving in city traffic, summarizing a story, and playing tennis, these are things that we do without having very software computation being done. But how do we do that? That says is basically perception, how we use perceptions. Perceive to perceptual distance, speed, direction, intent, other aspects. Okay. So limitations of today AI reflect the incapability of existing AI techniques to deal with perception-based information. To achieve human-level machine intelligence, it is necessary to endow AI with the capability to deal with perception-based information. That's what it says. So what is perception? You can easily see the difference. Here you're saying that temperature is 35 degrees. Here we are just saying it's a qualitative if it's warm. EY is 28, that's the age of a particular person. Here just saying that the person is young. So probability is 0.8, probability is high, like that. So very often we use this kind of qualitative information to think. That is, human thinking is not based on exact knowledge of any numbers. But this is very important. And what the modern AI techniques are using is trying to represent knowledge in this kind of format, that is perception-based format. And you can actually speed up the computation also very fast. Like this, just so what called a granular value is just instead of representing a single value of this, you represent as a as a larger space. You don't represent the exact value, you represent the rough value of that. So this is the idea. Okay, here you can see age. You can quantize age. You can age from lower stage to the higher age. You can say he is very young. He's getting middle aged, old, etc. But the same thing when it's granulated, you are representing it using something like a membership function. That means when you are between these this age 0 to this age, whatever it is, it shows it's called young. But then this young is overlapping with middle age, and middle age is overlapping with old age also. But this kind of concept, that is an ambiguous concept, we are able to use such ambiguity and still do a lot of processing. So this is another example of representing a function y, which initially a small value, then it goes up and then comes down. So that for various values of x and y. So here, that x value is quantized or small, medium, and large. Similarly, the y value is small, medium, and large. And in this case, when the representative function is in this way, this you can reduce the data requirement. Like if you want to store this information, you need to have the values of y and all these values, corresponding values of x. If there are 10 values of x, corresponding 10 values of y, you have to submit 20 different values you have to store. As here, we are just in a few numbers. Even this will do much better than this. That is the idea. Okay, this just a lot of information about various journals which use first years of computing in the titles. This was about 2006. This is what I discussed earlier also. So this is another area where a lot of work is done. There is natural language processing. So I will not go into detail. Basically, it is an attempt to store information about language on a computer and use that to modify that language or like converting stored in text to speech, speech to text. Similarly, one language to another, etc. All this can be done now. But I will not go into this. I think it's not enough time now. So these are the different aspects of natural language processing, lexical knowledge, syntax. So you need to have this kind of concepts to be able to process the meaning of any text or whatever. So how we convert some spoken words into text or into another language, it is a very complex concept, and it needs to be, it requires representation of concepts in a very complex way in a computer. So just example. Okay, so the NL natural language processing system has so many sites like morphological analysis. Is basically trying to identify different words like a noun, verb, adjectives, etc. Syntactic analysis is how the grammatical formulation is correct, the sentence is grammatically correct, etc. Semantic analysis is discussing what is the meaning attached to that, and this is a more deeper discourse integration, which means actually that you don't look at a single sentence, but look at the sentences which has come before and come after that, and try to understand the. So this is all very difficult thing even for human beings, but it's being done now. Okay. Now this is an just an example of machine translation. Earlier, people used to do statistical methods to find the best possible translation for a word. Now they are using neural machine translation, which basically uses deep learning. Okay. It is much closer to human thinking. Neural networks better capture the context full sentence before translating them. Entails high quality and more human sounding output. So the output also is much better than the statistical methods when you use neural deep learning methods. This is just, I thought I could add this also about machine learning. Beginning in Samuel, he started the first program, beat checkers. That is, he made a program to play checkers, and he could beat the masters, the checker master that time. But this same program now is able to do much more complicated, like it can play much more complex games like chess, and it can beat highly the top masters. You might have heard of a program called Deep Blue. It's able to defeat some of the top chess players in the world. Okay, so this is the summer, and the essential idea here is you are creating devices that can do things beyond what they are explicitly programmed to do. So this is a misconception many people have. Computers can do only what you have programmed it for. That's not true. Computers can be also made to effectively think like and modify its behavior like we human beings do. Okay? It's not just programming so that it can do. It's not monkey business. It's more than monkey business. So this is from 2016 conference Google presented one of its autonomous cars. So this car is without a driver. It's able to move on the road. In fact, nowadays, I think they in some US city they have a annual race where people with this kind of cars come and have races. Not only races, they move through very complex case of roads without hitting each other. So that's possible. You know. Hello. What happened? Something happened.
Yes, sir.
I don't know. Something happened. I think it had a link. Unfortunately, I think I pressed on it. I'll go back. Okay.
Okay, sir.
Are you saying that? Right?
Yes, sir,
You
it's
can see it
perfect, sir.
now? Okay. So unfortunately, I clicked on one of those links, which takes to that company's website. So in this about this Google's car, what one of the people have to say that there are two applications. One is that about how the data, all this data is being collected by the machine, and it is using that to perform. But then it's also not just using the data; it is also able to create new perceptions, and there it is using. This is mostly the old time, the conventional machine learning. Whereas here, they are using what is called neural network, convolutional neural network algorithm. That means uh, neural networks which not only learn but also relearn. So, and also it's also able to apparently, I don't understand it fully, but basically we say that it tried to test from the hardware that's available. And such systems are being built nowadays, which are mission critical. That means it is highly dependent on uh, highly critical kind of uh, depending on the machine. For example, if you want to launch missiles, etc., you need this kind of systems. We are the continuously updating software. The software is not something that is fixed that you have made. The software is modifying itself. So which of course is something like we also then robots are actually doing that also. Their behavior can be changed, even though we say that we are in control. We cannot be so sure that how exactly that modification will happen. So this method, deep learning, is something that I talked to you about. It is nothing but an extension of the neural network, but where a lot of feedback is used to uh, get better perception about the problem. Okay. So this is again what one of the people says, Chris, the company's Cadence company, Chris Noven says that you can have deep learning is all about making better guesses, but the nature of correctness is difficult to define. There is no way you get that right 100% of the time. That means it's effectively like a human being. It's trying to learn, trying to make guesses, but then whether the guess will be correct or wrong, that you cannot say. But what he also says is the more data you have, the better you are, because ultimately in these systems, the data that you input is what is being looked at, because there is no models being made there. It's all the data. It's just from the data, these systems are able to create new concepts and new algorithms. So that is the state of AI today. And of course, you might have seen some of the cases where the robots are made to dance to music, etc. They do various kind of things. If you go to Boston Dynamics website, you can see them doing that. I thought I will present it here, but there is no need. You can very well go to Neuronet, any internet website, and go to the, just click Boston Dynamics in Google, you can get that. So these are all things that I wanted to present to you. I don't know how coherent it was. I don't know how much of information you could get from what I have done. Thank you all for listening patiently. If you have any questions, you are welcome to ask me. Okay, that's all.
Thank you, sir. It was really an informative session. I'm sure everyone enjoyed this session. Now, this is Q&A session. If you have any doubt, please unmute your mic or text message in the chat box.
Anyone? Hello, sir.
Yeah, sir, no questions, sir. And I think you explained very simple, and the participants are happy with the
Okay.
yeah, with the talk.
I was told that it's going to be a BTech level student, undergraduate student. So yeah.
Yes, sir. It is that is we would like to have also. So thank you very much.
Yeah.
Now the team, please take over the team.
So finally, we are moving to our wind-up session. I invite Ardra Sujadan, Vice Chair of Women in Engineering, Student Branch, Musiliar College of Engineering, Chirangire, for word of thanks.
Good evening, Monitor. It's my privilege to propose vote of thanks on behalf of IEEE Education Society Kerala Chapter, Education Society SB Chapter, College of Engineering Perumon, and IEEE Student Band Chapter, Musiliar College of Engineering Chirangir. I extend my sincere thanks to Dr. Karthikeyan Chittayil for handling this session on artificial intelligence. We are thankful to you, sir, for taking out time for us and presenting such an informative session. Thank you so much, sir. I also extend my sincere thanks to Professor Muhammad Qasim, sir, Vice Chair, IEEE Kerala session, for all the support extended to us. Thank you so much, sir.
Thank you. Thank you.
Also, my sincere thanks to all the faculties and students who attended the session and make it success. Thank you, one and all.
Thank you, Ardra. Thank you all for participating in this session. Thank you, IEEE Student Branch of Musiliar College of Engineering, IEEE Education Society Kerala Chapter, College of Engineering Perumon, and IEEE Education Society Kerala Chapter. Thank you all.
Anandu, shall we have a photo session? If all the participants can unmute your video, we can have a photo session.
Yes, sir.
Yeah, please unmute your video. All of you, please, so that we will have a photo session.
What are requested to put on your videos, having a photo session. I request everyone to put on your videos for a photo session. Kasim sir, your mic is on mute. You are telling something.
Okay.
Karthikeyan sir ഒന്ന് ആ ലാപ്ടോപ്പ് ഒന്ന് അഡ്ജസ്റ്റ് ചെയ്താൽ സാറിനെ കുറച്ചും കൂടെ നന്നായിട്ട് കാണാൻ പറ്റും. Yeah, fine, sir.
It's okay, sir.
Mic mute on.
In
Can mute
3,
it, illa?
yes, sir. In 3, 2, 1, IEEE. Second, sir. Kasim sir, again your mic went muted.
Okay.
Yeah, thank you
You
all,
want me to
thank
mute
you
it,
very
illa?
much for joining this session. Let us hope to have more sessions jointly with College of Engineering, EdSoc SP chapter and Musiliar College of Engineering in future also. Thank you all. Thank you very much. Yeah, thank you Karthikeyan sir for your remarkable talk